So good morning. My name is Chipot. This morning I'm going to talk about frequency calculations. So just as a preamble, who is familiarized with frequency calculations? Just raise your hand. Okay. Yeah, yesterday I was passing by the tables at lunchtime. Not because there was free food, but because I just wanted to eavesdrop and see, and I heard people mentioning binding free energy. So some of you have already run free energy calculations, right? So who has never heard of free energy calculations? Okay. The reason I'm asking that is sometimes, in this kind of introductory workshops, we have the whole spectrum, like from what is this guy talking about to this is really boring, I'm not learning anything. So I'm going to try to make it as introductory as possible for those who have never heard, but also try to get some interesting information for those who have already run this kind of calculations. So let me start with the outline of the lecture today. So I think we have until 12:30, is that correct? With a pause, with a break at 10:30 or
12:20 is our maximum.
Okay.
But
and there is a break at 10 or 10:30.
I'm checking the program.
Okay. So so here's the outline of the lecture. So I'm going to give an introduction and why do we want to do free energy calculations. And then I've taken the liberty to basically break the separate free energy calculations into two classes. This is kind of an arbitrary classification. Alchemical transformations, where basically you transform a chemical compound into another chemical compound, and geometrical transformation, where you apply some changes in the geometry of the molecule. And then I will finish with some ongoing challenges, ongoing developments in the field of free energy calculations, and then some concluding remarks. I put here questions, but I beg you, whenever there is something that is unclear, just don't hesitate. Just raise your hand, and there's no stupid question. So usually, questions are interesting for everybody. So why do we do free energy calculations? Not because it's cool. But maybe there are some other reasons. So let me put that in some perspective. And let's journey back in 1957. That was the first MD simulation. This guy. You're going to see a lot of pictures today. I like to put some faces in my talk so that you know who were the key actors in the field. So this is Bernie Alder, and so he was the first one to publish a paper on molecular dynamic simulation, and that was like to study phase transition in very simple liquids. And that was pretty much the brute applications of the Newton's equations of motion. So in our journey in the past, 20 years after Bernie Alder first simulation, came Andy McCammon and Martin Karplus, 2013 Nobel laureate, for the first MD simulation applied to a small protein, and that was BPTI, bovine pancreatic trypsin inhibitor, over 8 picoseconds. That was done in vacuum, right? And it was a different time. There was have you guys heard about the CCAM? Does that ring a bell? The Centre Européen de Calcul Atomique et Moléculaire, the European Center for Atomic and Molecular Calculations. So they have workshops now pretty much all over Europe. I invite you actually to check out. There are some pretty cool workshops going on where you have a chance to. They're very specialized workshops. They usually take place over 5 days. But back then, in the 70s, they were all the workshops were held outside of Paris in Orsay, because there was a computer facility there. And people would come with a project. So it was not like just a workshop for like 5 days where everybody presents his own science. People would go there for 2 months and actually work on a project. And that's what these guys did. And that's basically how I would say like the scaffold of the CHARM program, MD, the MD part of the CHARM program, that's where it was born in 76, 77. And that's where they actually run their first MD simulation of a small protein. Okay, so keep that in mind, 8 picosecond, a small protein, 1977. And ever since, it's been a continuous race for the longest simulation, possibly with the biggest system. So here are the typical timescales that you are dealing with when you talk about MD simulation. So you have, as you can see, the size scale and the time scale are going in the opposite direction, because the larger the system, the shorter the simulation. So these are the typical objects that you can simulate, and the typical time scale that you deal with. So of course, box of water, you can simulate that for seconds. And currently, I think that this is the largest simulation ever endeavored. That's a whole cell or a whole protocell that was done here in the Schoten group. And so that's a billion atoms. Okay, that's you may have already seen these pictures. So this is the capsid of the HIV virus that was simulated over the microsecond timescale. And that's the ribosome, and that can be simulated also over microseconds. And then you have these small proteins that you can simulate over milliseconds today. We did, for instance, the Anton machine of the DE Show research group. Now, what's really interesting is more than these timescales and size scales are the typical timescales over which important movements, collective motion happen. So if you look on this scale here, we go from the picosecond timescale, and that's typically the reorientation time, the relaxation time for a water molecule to reorient in bulk liquid. To the nanosecond timescale, so that would be typically the spontaneous binding of a small drug to a protein. So what you see here is Tamiflu binding to H1N1 neuraminidase. That's the target for avian flu. To the microsecond timescale, and this is the infamous Billin headpiece that you may have heard of. This is a fast folder. It's been studied extensively. It started back in 1998 with Peter Coleman, the first microsecond simulation ever done, published in Science. They did 1 microsecond. They were still pretty far from the complete folding, but they were pretty far in a sense that they were just missing the final collapse of the third helix, which is actually the longest rate-limiting step on the folding pathway. The whole protein actually folds in 6 to 7 microseconds. 2 much longer timescales. This is a transporter. This is an ABC transporter, and the conformational change of this transporter, so it kind of carries or conveys substrate from one side of the membrane to the other side of the membrane, that takes place on the millisecond to the second timescale. So this is typically something not amenable to classical molecular dynamics. So this is the reason why you may want to use Trinity calculation. And you can see that as some kind of a computational tweezer to anatomize the system, to basically select degrees of freedom and act specifically on these degrees of freedom, okay? And let the rest of the system basically live its happy life, but you just touch specifically 1 or 2 degrees of freedom to accelerate sampling along these degrees of freedom, these selected degrees of freedom. So on the menu, what can we do with free energy calculations? So I was mentioning your mini days. So a class of applications for free energy calculation is all the recognition and association phenomena. So in this case, it's a small ligand binding a enzyme. Here, it's 2 proteins like binding together. This is barnase and bar star. You can also use free energy calculation to study transport phenomena. This is this protein is called GLPF. It's a member of the aquaporine family. Aquaporines were discovered by Peter Agre. Actually, they were extensively studied by Peter Agre, who received the Nobel Prize in 2003. These are channels, membrane channels that transport specifically water and small molecules, small alcohols. So GLPF actually transports water and glycerol. So it's called the glycerol facilitator. And in this movie, what you can see here, it's glycerol actually trying to find its way, and finally found its way, going through a selectivity filter. It's actually an amazing protein. I mean, nature is amazing, and you have this very simple selectivity filter made of 3 amino acids, and that will only let go molecules that are the size of glycerol and smaller. But then you can say, what about ions? Ions are smaller than water and glycerol. So they can actually go through, but just below you have another filter called the NPA filter, so asparagine, proline, alanine, and that will reverse the electric field and push back all the ions back to the vestibule so that they can never go across the membrane. And finally, well, the movie is already over, but you can also use this free energy calculation to do conformational transitions. So maybe I should play it again. So what you're going to see here is a molecule that is a protein that belongs to the family of sugar-binding proteins, which have a very simple conformational change. We call that a hinged bending motion. So basically, it bends like this. So it's open, and when the sugar comes, like a sugar tongue that you use, at a teapot, it kind of closes on the sugar. Right? So the sugar comes, so you have like the apo form of the protein. The sugar comes, binds to the protein, and the protein just closes on itself. And what you're seeing here in red is the open conformation, in green is the closed conformation, and in blue is the current conformation. And we are simulating, we are kind of navigating with a free energy calculation between the open and the closed form. And so you have 4 possible states. You have the apo open, you have the apo closed, you have the holo open, and you have the holo closed. Okay. So then the question is, what's the best method for a given problem? Because you have a variety of methods. So I classified free energy calculations into 2 categories. I mean, kind of large categories: alchemical transformation and geometrical transformations. But in these categories, you have like the actual methods, I mean, subcategories of methods. So the first category is methods that are based on histograms. So the idea here is you select your degree of freedom, and you kind of sample along this degree of freedom, and applying a bias along this degree. This is just a preamble. don't be scared. I'm going to go into the detail later on, but it's just like as an introduction. So you know what we're going to talk about. So my degree of freedom that I call psi, I will apply a bias, and then I will histogram. So I do my sampling, biasing along this degree of freedom. Then I get a bias distribution, and this probability distribution, or the free energy, is related to this probability distribution by a logarithm, and it's defined up to a constant, up to a constant value of the free energy. Then the second class is non-equilibrium work simulations. So that's the idea. You may have heard already about steered molecular dynamics simulation. So it's a molecular dynamics simulation to which you add an external force along a privileged direction. So in this case, this is a muscle protein. This is a titin protein that you have in your muscle. So when you contract your muscle, you basically unfold and refold the protein. And so we're kind of simulating the extension, right? So this is non-equilibrium. But back in 1997, Chris Jarzynski demonstrated that if you do an ensemble of realization whereby you actually pull irreversibly along the direction of your choice, you can show that if you are actually the paper doesn't say anything about the regime, but in practice, if you are in a regime that is close enough to equilibrium, then you can relate the free energy to an ensemble average over realization, over non-equilibrium work through an exponential. Again, I have to replay the slide, but just the animation. So far, everything clear for histograms and non-equilibrium methods?
I have one question.
Yeah, sure.
So when you do assembly molecular dynamics,
Mm-hmm.
and you pull your atom from one direction,
Mm-hmm.
so if you pull the same atom from different direction, you have different picture for free energy, right?
Yes, and actually, some people have proposed that as a way to get, for instance, binding free energies. And I'm going to talk about that a little bit later in the lecture, showing that it's not very efficient.
So the direction matters.
Direction matters, yes. The direction matters, especially for recognition association phenomena, where you actually pull the ligand away from the substrate, away from the protein. And so if you pull like this or if you pull like that, it's not the same. Okay, so that's non-equilibrium work simulations. And so the next category is perturbation theory. And as you can see here in this animation, we are transforming one species, one compound into another compound. So basically exploiting the malleability of the potential energy function. So we're just playing with numbers here. We're just changing some van der Waals parameters. We're just changing some charges to transform matter, just like the alchemist would do. And the equation that is usually used for that is the so-called perturbation formula due to Zwanzig and Landau, and which relates the free energy to the potential, to the exponential of the potential energy function, actually to the change in the potential energy function. And the last family of methods is the gradient-based method. So what we do here is we apply a force along a certain direction. So in this case, this is another transporter transporting ADP, ATP. And so in this case, we apply a force along the z direction. We measure the gradients of the free energy, and then we integrate it. And this is the kind of formula that we're using. I'm going to go in the detail of this. So we have like 4 very different methods, And depending on the problem that we have, one method is more efficient than the other. One method should be preferred. Yes?
But can all of these methods be adapted to work with activation-free energies, or only certain ones of them can be used for activation?
For activation?
Yeah.
By activation, you mean like study a reaction?
Like, yeah,
a barrier.
Yeah.
Well, usually, if you are interested in a barrier, for instance, in recognition association, you have like a host and a guest, right? And you're looking at the binding of the host to the guest, right? And there might be a barrier. Usually there is a barrier, right? But in this case, it's definitely geometrical. And in this case, probably perturbation theory is not the method that you should use, right? But we will see that we can actually do binding free energies with perturbation theory. But you get a different, shall we say, you get a different picture. You will get your binding free energy, but you may not get a profile with a barrier. I mean, what you will get is more like a number. Okay, so let me just try to get my point across with an example. So, as an illustration, I'm going to talk about the synthesis of protein by the ribosome, right? And so, as you may remember, nascent proteins insert in the membrane via the so-called sec translocon complex. So, if you're not familiar with that, let me explain to you briefly. What you see here, and that's only part of it, is the ribosome. And so the ribosome sits on the ER membrane, so the endoplasmic reticulum membrane, right, where its exit tunnel through which the synthesized protein chain comes out. This exit tunnel will meet a complex that is called the sec translocon complex. And this sec translocon complex is used to actually convey, or it's a channel actually through which the nascent chain goes. Now, what's nice about this complex is that it has a lateral gate, and depending on the signal sequence, the lateral gate will either open or close. So, if the ribosome synthesizes a membrane protein, the signal sequence will be such that it has to open, the lateral gate has to open, so that the nascent chain diffuses amidst the lipids, where it will meet, let's say, a chaperone that will help the folding into a functional membrane proteins. If, on the contrary, the ribosome synthesizes a hydrosoluble protein, then the lateral gate remains closed, and in that case, the chain goes through to the other side of the membrane, right? Another thing I'm gonna mention that again later on. But what's interesting about this sec translocon is that it has a special topology that looks like an hourglass, and so you have like this constriction region that kind of promotes secondary structures, so kind of helps pre-folding the nascent chain into secondary structure elements. Of course, like the final folding into a tertiary structure occurs on the other side of the membrane. Anyway, so, sorry. So, an interesting problem that was noted by theorists is that insertion of charged amino acid is what predicted by experiment is far less than what we think. So, for instance, an arginine only requires 2 to 3 kcal per mole according to experiment, which is kind of surprising because it's a charged amino acid going through membrane, and what simulations predict is 14 to 17 kcal per mole. And I'm going to show you that the first simulations that were done to arrive to this number may not be the most clever ones. So what they actually did is the following. So here's the setup. So the setup is a pseudo infinitely long alpha helix made of leucines crossing the bilayer, and one amino acid, one leucine side chain, has been replaced by an arginine side chain. And so we start with the arginine deep in water, okay, and then we apply a force to move the helix upwards. So what you see here, we're going in the z direction, so we're moving upwards. So we anchor the potential of means for the free energy profile at 0 when the arginine is in waters, dehydrated. And as we move, of course, when arginine goes into the bilayer, the free energy just climbs. And what we expect is when we pass z equals 0, which is the center of the bilayer, and we go on the other side, we get a almost symmetrical potential mean force. That's kind of a safeguard. If you don't get a symmetrical potential mean force, that means that probably your system is not properly equilibrated. So what you see here is the arginine side chain is already in the bilayer, but we have a lot of snorkeling. I mean, the arginine doesn't like to go naked in the bilayer, because that would correspond to a high free energy penalty to the dehydration of an ion. It usually comes with a lot of water, and you can see that here, which causes a lot of distortion in the bilayer. Actually, if you read the fine print and if you go to the supplementary material of the paper, you realize that they had to reconstruct the system at every step of the way. If you just pull even very slowly, you really mess up the membrane. So what they did is actually they shift the side chain, rebuild the bilayer, re-equilibrate, and then do the sampling to get the free energy. And what we think, and actually this is what we did, we think that this is, first, it's very costly, it's very inefficient, and you can get the same results doing the following, using, instead of doing a geometrical transformation, doing an alchemical transformation. And how do we do that? Well, we have this kind of a simulation box with the bilayer, with the pseudo infinitely long alpha helix. But what we have here are these two red dots corresponds to two leucine side chains that are hybrid. By hybrid, I mean that they have two side chains. One side chain is a leucine and one side chain is an arginine. So, and only one is visible. We cannot have the two at the same time. That would kind of violate the rules of chemistry, right? So when we have arginine here, we have leucine there. And when we have arginine here, we have leucine there. So what we do is we navigate between the two and we calculate the free energy change between the two. Okay. And of course, we managed to reconcile theory with experiments invoking, which is not done in this work, invoking the translocon. So doing the same transformation, the same alchemical transformation, not only in the bilayer, but also in the sec translocon, and showing that the sec translocon provides a more hospitable environment than the membrane, provides actually an environment that is kind of halfway between water and membrane. It's kind of an intermediate environment. Okay, so now I'm going to move to alchemical free energy calculations. And so I was just mentioning how we can calculate a free energy change with hybrid amino acid. Yes.
But then, when this
So the other one gave relatively wrong result, or result that was the job. But methodologically, there was nothing wrong with it. Why is,
No, I mean,
where does
the method is not wrong. I mean, there's nothing ludicrous about it. Just that it's very inefficient. I mean, we will see later on in the lecture that you can, since free energy is a state function, it doesn't really depend on the path that you choose to calculate it. You can choose the most ridiculous pathway to calculate your free energy, but by virtue of the state function, by virtue of the fact that it's a state function, you will still get the correct free energy, right? But it will take maybe forever to converge. Whereas if you choose I would say, a more clever pathway or a more clever method, then you will save quite a bit of time.
So the large convergence in experiment and simulation is because of lack of documentation?
No. I know it's a little bit confusing. The divergent or the discrepant result, the discrepant theoretical results, comes from the fact that they completely ignored in their simulation the translocon. That they just imagined that insertion of arginine occurs like this. That you just insert an arginine in the bilayer as part of a sequence of amino acids, right? Whereas what happens in reality is that when the protein chain is synthesized, it doesn't go in the bilayer like this. It goes through a channel, a specialized channel, which is called sec translocon. Yeah.
So, like the alchemical, you are having two side chains at the same time, and you calculate with respect to one at a time.
I'm gonna go to that.
Oh, okay.
Give me just 1 second, and we're gonna go to that. And if it doesn't answer your question, then you can stop. So who are these guys? So here you have Bill Jorgensen. So Jorgensen is famous in the field of simulations. I mean, you may have heard of him. I hope that you have heard of him. This is the guy of tip 3P, tip 4P water models of the OPLS force field. He's also the guy who did the first alchemical transformation. So he basically was the first to apply perturbation theory to the calculation of to calculate a free energy change between two compounds. So it was 1985, Jorgensen and Ravi Mohan, and they did methanol to ethane. And it's actually amazing that back then in 1985, so 30 years ago, they were able to be so close to experiment. In retrospect, Bill Jorgensen admits that it was probably a fortuitous cancellation of errors, like too short a simulation and too crappy a force field. But still, I mean, it was kind of a very nice proof of concept that you could apply successfully perturbation theory. This is Peter Coleman, who actually, when he saw the first successes of application of perturbation theory to alchemical transformation, then he used it for the first side chain mutation, first amino acid mutation in a protein, and also for the estimation of amino acid side chain hydration free energies. Those are like the two science papers that he did back to back in 1987. So though that was the kind of a golden age of free energy calculation, the very beginning of this calculation. Finally, Herman Berenson, who you may also have heard of, this is the author of also Peter Coleman is the author of AMBER and the AMBER force field, AMBER program, and Herman Berenson is the author of Bromos force field. Bromos And finally, Gromax. He was kind of the guy who inspired Gromax shortly before he retired. So why Bill Jorgensen and Peter Coleman on this slide? So how did they do this alchemical transformation? So the paradigm that they were using back then is the so-called single topology paradigm, which is a little bit different from the idea of having a hybrid amino acid, which I'm going to present afterwards. So the idea of the single topology paradigm is you have one topology that is a common denominator of the two states. So you have to find maybe again I played that too fast. You have to find what is the common denominator. So in the case of methane to methanol to ethane, you have to find what is the topology that kind of encompasses the two states. So obviously that would be ethane, right? So here I'm showing the transformation of a serine side chain. Actually, no, this is not. That's not serine. That's not just an alcohol. And so what we do here is we're transforming it into a CH. So we're transforming the hydroxyl group into a methyl group. So the methyl group will actually be the common denominator. So what we do here is we're transforming the charge of the carbon into a charge of the hydrogen. The charge of this hydrogen in the context of an aliphatic compound into a hydroxyl hydrogen charge. These guys will disappear, so we turn the charges to zero. And also we're going to turn the van der Waals of these guys to zero, right? Another thing that we have to do is we have to change the bond lengths. So we go from a CO to a CC bond length, so something like 1.4 to 1.55 angstrom, right? So, and how do we do that? Well, we use a general extent parameter, sometimes it's called coupling parameter, that goes from 0 to 1, and we scale the charge, so it's a linear combination of the charge of the initial state with the charge of the final state, something like Q final times lambda plus 1 minus lambda Q initial, right? And we do the same thing for the van der Waals parameters. If you shake the bonds, so you know what shake is, right? Shake, rattle. Those are like this algorithm that we use to constrain. So holonomic constraint, not to be confused with restraints. So hard constraints. So basically, we eliminate this degree of freedom. So if the bonds are shaken, then we need to calculate. We need to do an extra calculation, a potential of mean force calculation, whereby we're actually shrinking or dilating the bond length, calculate the reversible work that is needed to increase or reduce the bond length. And it requires some electrostatic decoupling. You never want to have a naked charge. So before turning the van der Waals to zero, you need to remove the charge. Otherwise, you have like these charges with no van der Waals that will collide with all the other atoms, which creates instabilities in the trajectories. Okay. So that's what we always do. And actually, we have a safeguard in NAND. You cannot actually have naked charges. You will always have van der Waals. You will always remove the electrostatics faster than you do the van der Waals. So this is the so-called single topology paradigm. And so the other paradigm is the dual topology paradigm, and that's from the Karplus group with Jiali Gao. And so the idea here is to define concomitantly the initial state and the final state, right? So so this is how it's done. So we transform, we make the initial state disappear at the same time as the final state appears. But when you construct your topology, I mean, you will see the two states. I mean, they are defined. So it's basically a carbon that has 5 bonds, right? It's pentavalent, but it's not pentavalent. It's actually tetravalent, because the two side chains of the initial state and the final state do not see each other. Okay, they see the environment, but not at the same time. Okay, and here, instead of transforming the non-bonded parameters, so instead of scaling the charges and the van der Waals, what we actually scale is the potential energy function. Okay, so again, U final times lambda plus 1 minus lambda U initial. Okay, so it's prone to endpoint catastrophes. So what does it mean? You have to be careful when you do that. When you make the final state. So you start from the initial state and you make the final state appear. You have to be careful because it can appear in a part of space that is already occupied by other molecules, other atoms. And that creates immediately a singularity in the van der Waals potential. So again, we're going to talk about that later in the lecture. We have tricks to solve that. It's called the soft core potential, which is implemented in MD. Another way that's what we used to do in the past, is use very fine increments of lambda, but now it's not necessary anymore. We just shift and scale the potential and to solve the problem. Now, if you have to build your own topology, if you have want to define a new molecule, say a drug, and do a relative free energy calculation. So to go from, imagine like you have 2 congeneric drugs, and you want to just mutate part of the drug and calculate the relative free energy when it's bound to a protein. So you have to define your own topology. Branching requires particular care. So branching, that's where basically you define your hybrid, your initial state and your final state. So if you look at this example here, and you want to do the transformation of a methyl into a hydroxyl, could we do the branching here just before the methyl or the hydroxyl? And the answer is probably not, because if you calculate the charges, you will see that you have a charge of minus 18 here, whereas here you have a charge of plus 0.005 because you have an electronegative or an electroattractor group, right? So it's kind of sucking the charge distribution. So probably you want to branch and create your hybrid one step above. Okay, so probably like the carbon. Okay, that clear? All right. So now you have the 2 paradigms. So you know how to transform one state into another state. So once you know how to do that, then you need to do the calculation. And so I was mentioning free energy perturbation. So here are the guys who basically devised free energy perturbation theory. So this is Lev Landau back in 1938, and this is Bob Swansig. Actually, this formula is often referred to the Swansig formula, but if you go back to the Landau-Lifshitz book, you'll find that most of the theory had already been devised back in 1938. The Swansig paper is 1954. The beauty of this formula is that it only requires knowledge of the reference state. So basically what you do is you do a simulation with your reference state, with your initial states. You generate a long trajectory. And at each step of the way, you infer a perturbation. Okay? So you do like so you run your trajectory with respect to the reference state, which I usually note 0, and you do this perturbation, and you calculate delta U, so the difference between the final state and the initial state, right? And in the end, at the end of the trajectory, what you do is you do your ensemble average over the exponential of the delta U, so this little increments, this little perturbation, and that will give you the free energy change. So in practice, imagine that you have an ion, and you want to calculate the hydration free energy of this ion. So basically, what you will do is you generate a trajectory that will be your reference state, right? So you generate a trajectory with this reference state, and at each step, at each time step, you calculate difference in potential energy. So what's the change between this and that? So if it's, let's say, a monovalent ion, the charge is the same. So the only thing that changes is the van der Waals radius. So your delta U is just a change in the van der Waals radius. So you generate your trajectory, and at each step, you calculate the value of the potential energy with the initial van der Waals radius, and the potential energy with the final van der Waals radius. And then at the end, you just calculate your ensemble average, your exponential of minus delta V over the entire trajectory. Now, what John Kirkwood proposed back in 1935 is something quite equivalent to the perturbation formula. This is called the thermodynamic integration. And you can show formally that it gives the same answer. So what we calculate here is an ensemble average over the gradient of the potential energy, also with respect to lambda. Yes.
In terms of the plotting, the perturbation could be just in terms of position, or
we can actually use perturbation theory for geometrical changes. I mean, that's why, sometimes people kind of get confused. Perturbation theory, alchemical transformation, geometrical transformation, maybe gradient-based method. No, you can actually apply perturbation theory to geometrical changes. I mean, it's possible. Yes, absolutely.
but for alchemical, it would be turn a part of the protein.
So for alchemical, usually it's good to, a lot of people use perturbation theory, although you can use also thermodynamic integration. But if you look at the literature, I would say that most people use FEP methods. Okay, so now let's go into the physics of what's happening when you do this kind of calculation. I'd like to explain to you what's the real problem. Why are these calculations difficult? Why they are slow converging? So, but the first question is, so how to deal with large perturbations. So let's take the perturbation formula and transform it. Let's do rewrite it. And so here what we do is we integrate over the variation of potential energy. So when we do that, then we need to introduce this probability distribution function, which you can see that as a density of state. And so, okay, so we're going to simplify the problem. Let's imagine that the world is ideal and that this distribution is Gaussian. So, and let's plot P0 of delta U. So we do a sampling, and and we plot according to the value of delta U, the perturbation, right? So this is my distribution P0 of delta U. Now we're going to multiply that by the Boltzmann weight, okay? So the product of a Gaussian by an exponential is a Gaussian, right? But a Gaussian that will be, in this case, shifted to the left towards more negative energies. And this is where the problem lies. So imagine that, so this is my distribution. I've done my sampling, okay? I'm plotting my density of state. Here I'm multiplying by exponential minus beta delta U. And this is the final curve, okay? Now, you will notice here that this product only partially overlaps with P0 of delta U. What does it mean? It means that all this region here corresponds to values of the perturbation delta U that I have not sampled, because what I've really sampled is this. Okay. So it means that my free energy will have a certain component of error, because all this part of the product lies in a region for which I have no statistics. Okay. So what does it mean? It means that the larger the variance, the larger the spread of the curve, the larger the perturbation, the larger the variance, right? The more shifted the product P0 delta U times exponential minus beta delta U will be towards regions for which I have no statistics. Okay? In other words, you have to be very careful about the choice of your delta U, the choice of the magnitude of the perturbation that you apply. Okay? Otherwise, you fall you end up in a region for which you have no statistics, and then your free energy is meaningless. Okay. Yeah.
Could you explain the delta U in a more simpler way?
So delta U. So I gave an example before of probably like the most simple example that you can imagine. Hydration free energy of a small solute, in that case an ion. I take an ion, and I say a monovalent ion, so the only thing that changes is the van der Waals radius. That will be my delta U. The delta U will be, in that case, the change in the van der Waals radius between the initial state and the final state. Okay. You agree with me that if I calculate, let's say that, okay, I will make it even more concrete. I want to calculate the differential hydration free energy of between lithium and sodium. Both are monovalent. Okay. The only thing that changes is the van der Waals radius. So what I do is I generate. So my initial state is lithium in water. I generate a trajectory. So my lithium is moving around in my box of water. At each time step, I calculate the potential energy with the van der Waals radius of lithium. I also calculate the potential energy for sodium with water. Okay, so kind of infer the perturbation. Okay? So then I get a delta U. The delta U would be the potential energy for sodium minus the potential energy for lithium. I do that at step 1. I do the same thing at step 2, step 3, all the way to the end of the trajectory. At the end of the trajectory, I calculate exponential minus beta delta U, and I average that over the entire trajectory. And that gives me the differential hydration free energy. Is that clear? Yes?
So if I take a transition, let's say one thing point, make it down into multiple steps.
I'm going to go to that.
Yeah,
I'm going to.
The question would be like, can I recover the loss on
Yes. I'm going to go to that. Yeah. You anticipate. I'm coming to that. Okay, so this is exactly what Abhishek was coming to. So imagine that this now I'm going to, let's say, something a little bit more crazy. I'm going from lithium to rubidium. But now the change in the van der Waals radius is more substantial. And maybe I cannot do it in one step. And actually, maybe I'm going to be in that situation. If I'm plotting P0 delta U and the product with the Boltzmann weight, then I'm finding that I have too much data. I mean that too much of the curve that is in a region for which I have no statistics. Then I want to do stratification. Stratification means that I will have to introduce some intermediate steps, intermediate states. And that's where I'm using this lambda variable, this coupling parameter, to take me slowly from lithium to rubidium by small increments of the van der Waals radius. And then by extension, I can do that for anything. I can do that for charges, I can do that for bond lengths, you name it. And so the idea here is that when I have my ensemble representative of the initial state and the ensemble representative of the final state that do not overlap, then I introduce these intermediate states so that each pair of contiguous states mutually overlap. And then then I know that the accuracy of my free energy calculation would be acceptable. I know it's a little bit tricky, but it's important that you understand this. Yep.
You take your lambda as a finite state, and so that you make your perturbation slowly to get all the samples. That's what you.
Yeah. What you want is, you don't want to be in a situation like this where you have where the overlap is only partial, right? You really want to have a full overlap, and the only way you can do that, you have to just remember one thing. If you think in terms of distribution and variance, the perturbation is related to the variance is related to the magnitude of the perturbation. The larger the perturbation, the larger the variance, right? And you know that in the Gaussian case, when you multiply the Gaussian distribution by an exponential, you get another Gaussian distribution that is shifted, and that this shift is related, or actually is a function of the variance. Okay, it's shifting with respect to the peak. With this average of delta U0, you're shifting by this quantity. So the larger the perturbation, the larger the shift. Okay, and the more prone you are to end up in a region of delta U, for which you have no data because you haven't visited it in the course of the simulation. Hence, the introduction of intermediate states to guarantee that pairs of contiguous states will mutually overlap. Yes?
In case of bond length, then you're almost like moving along a reaction corridor where you're separating a little bit, like sampling at each small separation, right? Mm-hmm. So that's basically the main idea, but with any other magnitude I would want.
Yeah.
Okay.
Yeah, absolutely. If you got that point, that previous slide, I know I was a little bit long on that slide, but if you understand the previous slide, you understand everything. So then the question is, how many strata, how many intermediate states should I use? So this is a transformation, very simple system. This is argon, so a noble gas in water. I want to calculate the hydrophobic hydration of argon. And I used 4 windows to go from, so the way we calculate it, usually when we want to do hydration for energy, we just make it disappear or appear in a box of water. And we do the same thing in vacuum. I'll explain why. So this is in water. And what I did here is I did, just to make my point cogent, I did the simulation reversibly. I did it forward and backwards. So I create and I annihilate. And I should get the same result, right? I mean, with a minus sign. I should get the same delta G, the same hydration free energy, but with a minus sign. And I plotted the P0. So I call P0 usually the probability distribution for the forward transformation and P1 for the backward transformation, right? And I should get an overlap in the different windows. And as you can see here, I'm pretty far from it. And if actually I calculate the free energy, I get a huge hysteresis. So instead of getting delta G forward equal minus delta G backward, I get numbers that are completely different. And that can be understood by just looking at these distributions. Now, if on the contrary, I'm a little bit more generous and I stratified with 16 intermediate states, you can see that it's a completely different story now. The forward and the backward transformation overlap nicely. And now I'm pretty guaranteed that my free energies will, my free energy calculation has converged. And indeed, if I look at the final result, my backward and my forward transformation coincide. I'm going to put here and there. I'm going to put the NAMD lingo for that you're going to use in the tutorial. So. Coming with the free energy calculations, we have a script called fep.tcl that you just need to invoke by source fep.tcl. And so when you type run fep 01.0625 $ and steps, it means that you will run fep between lambda equals 0 to lambda equals 1, so initial state, final state, with an increment of 0.0625, which is 1 over 16. So if you're going to use 16 windows, and for each of these windows, you're going to run n steps. Okay. Now I'm going to mention something pretty important when you do this calculation. I mean, try to give you some good practices. That guy is a famous guy. His name is Charles Bennett. He works at IBM, or he used to work. I think he's retired now. He was famous for something completely different from free energy calculation. That's actually his contribution to free energy calculations. I think is I don't know if it was like a side project or that guy worked actually on teleportation of photons. So something completely different from free energy calculations. But he's very famous for one thing, for the so-called BAR, Bennett acceptance ratio. What's the Bennett acceptance ratio? It's a maximum likelihood estimator of the free energy change. So basically what we're trying to do here is we're trying to minimize the variance. And what Bennett showed is that if you combine the data from a forward and a backward transformation, you're actually reducing this variance. So that's one of the good practices when you do free energy perturbation calculations. Just don't use the FEP estimator. First, do always a bidirectional transformation. First, it's a nice safeguard because it will tell you if there is some hysteresis, you know that there is something not quite right. Probably your sampling is not adequate. Second, by combining the forward and the backward, the statistical data from the forward and backward transformation, you will reduce your variance quite a bit. Okay. And the good news, so the way it works is actually you have to solve iteratively this set of equation. You don't know what delta A bar is. I mean, the Bennett acceptance ratio for energy. You don't know what it is a priori. Neither do you know what this constant C is. So you have to you have to bootstrap the calculation. And usually we bootstrap it with the FEP estimator, which you get readily from your free energy calculation, from your FEP calculation. And then once you bootstrap that, so you know what N1 and N0 are, those are like the sampling size, then you can iterate and get the bar free energy. The good news is that the math is done to get also the variance, so you get the statistical error associated to the estimator. So that's pretty cool. And the good news also is that you don't have to do that by hand. All of this is available in a plugin that is in VMD called Parse FEP. So you just go to go to VMD, you invoke Parse FEP with your NAMD output, and just let yourself guided by the plugin. What you can do also is, and it's something that we haven't quite finished putting in NAMD, is double wide sampling. So instead of having to run separately the forward and the backward transformation, you could actually run them at the same time. So for each intermediate states, for each lambda state, you calculate the forward free energy and the backward free energy. There's a little gain actually in doing that. In terms of efficiency, you gain about 20%. One thing that is super important that you have to keep in mind, so we stratify, so it means that we're running, for all intents and purposes, when you stratify, you're running independent simulation. But for you, it's going to be transparent because NAMD is going to run from 0 to 1. But literally, what you're doing is you're running one simulation from 0 to, let's say, 0.0625, from 0.0625 to 1.35, etc., etc. So for each individual simulation, if you remember, I was mentioning that this FEP.tcl run FEP 0 to 1 with the increment and the number of steps. So this number of steps actually embraces an equilibration stage and a data collection stage. So the way things work in NAMD is at each lambda state, you do a thermalization, and after the thermalization, you do a data collection. The thermalization is basically you kind of cleaning the slate, and once it's done, once the system is properly thermalized, then you're doing your data collection, and it's only the data, it's only that part of the simulation that you're using to calculate your ensemble average. Why do you need to thermalize? Well, it's very simple. If you don't thermalize, you have a memory effect, which is often referred to as Hamiltonian lag. So imagine that you are at the first stratum, the first state of your transformation. So your system is kind of representative of let's say, I'm going to go back to the example of lithium to rubidium. So your system is representative of the lithium solvated by water. Okay? Then you're going to the next lambda state. So now you have increased a little bit the van der Waals radius. You need to re-thermalize the system so that it doesn't remember configurations representative of lithium. Now it has to be representative of lithium a little bit bigger than lithium, right? And so on and so forth. Otherwise, you just accumulate errors all the way, and this error will just keep growing and growing and growing. So it's very important that the system is re-equilibrated at each step of the way. Okay? You wanted to ask a question?
Yeah, so when you were saying re-equilibrated, like, are you saying, like, we do multiple steps, or we do like the?
Yeah, exactly. So we have like, so you have num steps,
Yeah.
which is the number of steps per lambda state, and that includes alk equal steps. So if you say like num steps is 100,000 and alk equal steps is 50,000, it means that the 50,000 first steps will be equilibration. They will go to the garbage, and then the next 50,000 will be used to do the ensemble average. Okay?
Those, just a question, those equilibration steps are at the same temperature.
Yes, everything is at the
That's
same
100%.
temperature. Yeah, absolutely.
Yes,
Yeah.
this equilibration will needed to be done in order to bring the density uniform.
It's just the main reason why you want to rethermalize at each lambda state is really to remove any memory of the previous state. You really want your Hamiltonian to be the Hamiltonian corresponding to that lambda state, and not the Hamiltonian corresponding to previous states. You don't want your ensemble of configurations to be representative of something from the past. You want your ensemble of configurations to be representative of what's happening now, that lambda state. Okay. So I was mentioning parse FEP. So parse FEP is the plugin that you want to use. So you just go, once you've done your free energy calculation, you just go to VMP. And so what's nice about parse FEP is that it will show you. So you have like something, you have like a visual safeguard by looking at the evolution of your free energy as a function of time, so how it converges, and you can compare the forward and the backward. It will also show you the probability distribution, and then you will do a number of calculations, so the bar estimator, the error, and so on and so forth. You may remember that I mentioned endpoint catastrophes. So basically, when you have like dual topology and you're making the final state appear, and suddenly it appears where in a locus that is already occupied by, let's say, water, then you have immediately like van der Waals clashes and boom, and the job stops. So to avoid that, to avoid these singularities in the van der Waals potential, we have a trick which is called soft core potential or shift scale potential. So we're basically rewriting the van der Waals potential, introducing this alpha here and this lambda here. So that basically will kind of rescale and shift the potential to avoid this clashes. So this is the so-called shift scale potential from Zacharias, and this is Andy McCammon. There is an equivalent from the Van Gunstrom group. Interestingly enough, they were published the same year. So this is what you basically get. So you're really shifting your van der Waals potential. And in the NAMD lingo, this is controlled by this parameter, alk van der Waals shift correlation. And we have like I think that the default value is 5, and I would say that for most cases it's fine. In principle, your free energy shouldn't depend too much on that. It shouldn't depend at all on that. Okay, so now in practice, what do you need to run an FEP calculation with NAMD? So you need an equilibrated simulation. So that's the prerequisite. You want to do an FEP calculation, you need to have a system that is properly thermalized, okay, in a preliminary simulation. And so what you're getting at the end of that is the usual Cartesian.core velocities.vel extended system.xsc. The extended system is the file that contains the size of the box. Right? Then you need, of course, the PSF file, the structure file, and the NAMD file. So this PSF file is actually not quite standard file. That's the file that actually will contain, so when we have, like, for instance, hybrid topologies, sorry, you have to make sure that in this file, it's a kind of clean file. When you have a hybrid topology, so when you have, like, pentavalent site, alpha carbon, right? You want to be sure that you have an exclusion list that say you don't want the two side chains to see each other, right? So the atoms of the initial state and the atoms of the final state should be kind of excluded. They should not see each other. They should not interact, either directly or indirectly. So directly through non-bonded interactions, or indirectly through bonded interactions, for instance, through dihedral angles or valence angles. So you need, of course, the NAMD config file, and you need an FEP file. So what's an FEP file? That's basically a clone of your PDB file. And in either the X, Y, Z, O, or B column, you have a flag. So this flag can be -1 for departing particles, +1 for incoming particles, 0 for unchanged particles. So for instance, you're changing, let's say, an alanine to a glutamic acid. So for the alanine, you're going to put, for the side chain of the alanine, you're going to put a -1. For CH3, you're going to put -1. And for the glutamic acid, for the side chain, you're going to put a +1. So that's NAMD knows, and for the rest, of course, you're going to put 0. So NAMD knows that going from 0 to 1, lambda equals 0 to lambda equals 1, it has to make the CH3 of the alanine disappear, and the CH2, CH2, COOH, or COO minus appear. Okay? I know it's a lot of information. Everything clear so far? And so, you run NAMD, and then you get a FEP out file, and of course the usual log file. So the FEP out file is the file that you will use with sparse FEP to do the post-treatment, to calculate your bar, your Bennett acceptance ratio estimator, to show your probability distribution functions. Just a sec. And so of course, the more data you have in the FEP out file, the better. Ideally, you would like to write every step in the FEP out file. In practice, you know, it's not always desirable to have too many input-outputs. Too much writing for the efficiency of the code. Let's say like every 10 steps, every 20 steps, but you don't want to skimp. I mean, basically that's the idea. Otherwise, you're kind of losing accuracy in your post-treatment, right? Yes, I'm sorry.
So do you have control when you're doing a mutation, for example, and you want to then, if it's a big change, you want to have several steps? Can you decide what changes in each of the steps, or the program decides how to allow them?
No. I'm afraid, that's user-defined. And so I try to illustrate that, with the example of argon, appearing in a box of water, and showing that, you use 4 windows and it's horrible, and you use 16 windows, it's much better. I'm afraid it's something you have to try. I mean, of course, after a while, you can make like some educated guesses, and you're kind of used to it. You kind of anticipate how many strata you need, but it's tough. But one thing, and I didn't say that so far, but you shouldn't think. I mean, if with any luck you know the result already, you shouldn't think in terms of free energy change. let's say, you shouldn't say, oh, this is like a small free energy change, so I don't need too many strata. That's wrong thinking. Let me give you an example. Hydration free energy of benzene, minus 0.8 kcal per mole. It's slightly negative. It's pretty big and hydrophobic, but you have a quadrupole, and so you have like favorable dispersion interaction, and you have a little bit of electrostatics that's kind of favorable. So minus 0.8, that's not much, almost kT. So maybe, with a few windows, that should do the trick. And it doesn't. And the reason it doesn't is because it's big, and there is a lot of, when you make benzene appear in bulk water, there's a lot of reorganization of the solvent around the solute going on, and so for that you need quite a bit of strata to get converged free energy. So don't think in terms of the final delta G. Think in terms of the magnitude of the perturbation and the reorganization of the environment incurred, or the reorganization incurred by in the environment due to the perturbation. Yes?
Detailed question. So here we have the PSF file and the Alchem file. I think both of them describes the structure. I'm just wondering, for the PSF, is it describes the structure before the change or after the change?
So yeah, it's actually it's both. It's both. Yeah.
So the NAMD reads the PSF first, then apply the Alchem file to the PSF. Like, because you said you can introduce some group or remove some group in the Alchem file.
So your PSF actually contains the topologies that are required for your alchemical transformation. So imagine that you have a protein, and you're interested in changing one amino acid in that protein. So one of the amino acids will have indeed 2 side chains, and these will be in your PSF file. But it will also have the information so that these 2 side chains don't see each other. Okay.
So it's a kind of a special or odd PSF.
It's not a conventional PSF. Although I want to say something. So we have a code that is that cleans the PSF, but NAMD also does it. I mean, so if you just want to generate a regular PSF, a dirty PSF, where you don't have this exclusion list, in principle, when you run NAMD, it will take care of that, because NAMD includes that part that alchemify, which kind of cleans up, takes care of the exclusion list for the non-bonded and the bonded terms, the undesirable non-bonded and bonded terms. Yeah. No, not yet. I'm almost done. So the first example that you will see this afternoon in the tutorial is a zero free energy change. So that's kind of a nice example, because you know what the answer is. We're going from ethane to ethane. So by making one CH3 disappear at one end and reappear at the other end. So we know that it should be great. So this is just to show you. I mean, this is the topology file, the typical topology file. So we have a block for the initial state. So for the initial CH3, the one that will disappear, we have a block for the one that will vanish, the one that will appear, and then we have the common denominator here, it's actually a CH2 with 2 hydrogens, and to basically, so we have this part here, and then we have this group here that will appear, and this group here that will disappear. And so, as I said before, if you look at the free energy change as a function of lambda, when you go from lambda equals 0 to lambda equals 1, well, that's a net free energy change of 0. And as a safeguard, we're going to do that backward, and also we get something close to 0. So that's, yes?
Okay, that I do have to make it manually or?
No, it's provided. It's provided, but it's kind of nice to know how to do it. I mean, if you have to do it, or if you have to alter, if you have, for instance, an amino acid. For instance, I had to do it, so maybe you will use it this afternoon. So we have a library of all the amino acid hybrids. So if you have like 20 naturally occurring amino acids, then you have like 20 times 19 divided by 2 possible mutants. And so I had to use this, basically alter the side chains pseudo manually.
But there is any sort of generated topology that has to be done.
Well, if it's like something completely new, then you'll have to do it. Then you will have to do it yourself. But I mean, usually you start with something. You start with some topology, and then you add. So, for instance, here you take the topology of ethane, and then you just play a little bit with the file and add modify it. So just to define what's going, what's up here, what's incoming, and what's outgoing. Right. Okay, so now we come into a tricky part. So you remember what I said about you always want to make the van der Waals, or you don't want to have a naked charge. So you will always want to have more van der Waals than electrostatics. So we have a scheduler when we do these transformations, and this scheduler is controlled by alg van der Waals lambda end and alg elec lambda start. That's the NAMD lingo. So imagine that we have outgoing particles. So how does it work? So for the electrostatics, we're going to start at lambda equal 0. Okay. So lambda equals 0. So we have the full electrostatics, and we make it disappear. So we have chosen here as an example 0.5. So we're going from 0 to 1 minus 0.5, which is 0.5. So that's what we're going to have. And then after that, the electrostatics is 0. Okay, there is nothing after lambda equals 0.5. And for the van der Waals, we start at 1 minus lambda van der Waals n, so 0.7. So we start at 0.3. And we go all the way to lambda equals 1. So as you can see, again, we're making the electrostatics disappear much faster than the van der Waals. Okay? And that's exactly what we want. And it's the same for the incoming particles. You want the van der Waals to appear much faster than the electrostatics. So as you can see, we start to make the van der Waals, we start to make the electrostatic appear when we already are at 0.7 for the van der Waals. Okay. No question.
Why is that? Sorry, I mean that's the first part.
Are you like why do we want to do that?
Yeah. Yes.
Because you never want to have a naked charge, a charge with no van der Waals. Because if you have a charge with no van der Waals, then there is nothing to protect it, right? So it will just crash against the other atoms, which creates instabilities in the trajectory, and basically causes your job to stop future. Right? So you always want to have some protection. Yes?
So what happens if treatment causes a loss of geometry?
A loss of what?
Geometry. like the loss of the structure itself. Because electrostatics are gradually going van der Waals to this or not. It's not like the real electrostatics and van der Waals that takes might be.
We're not touching here. We're not touching the bonded terms. So
the bonded term still retains.
no, we're not scaling that. You could actually. Brian introduced that, but we're not doing it.
And so mostly in your experience, this does not control geometries or.
No, in principle, no.